Well, today we are happy to have Dr. Ed Hansen, fairly recently retired from Hope College Department of Environmental, Geological and Environmental Sciences, and also a HASP member. He taught at Hope College for 35 years, and in recent years, his main research interest has been the geology of the Laurentian Great Lakes, focusing on climate reconstructions of the region during the last 6,000 years. So Ed, let's get the room heated up with some talk about climate change. I came prepared. Please welcome.
Well, thanks, Linda. I first met Linda when I was probably maybe 22, and she was a graduate student, and I was an undergraduate at the University of Cincinnati in geology. So we're going to focus on the past, at least initially. The title of the course is Past as the Key to the Future. Subtitle, What the Study of Climate and Climate Change in the Past Can Tell Us About Climate Change in the Future. Now, there's a lot of talk about how the climate is going to change, but a lot of that is completely divorced from what we know about how climate has changed in the past. Paleoclimatologists, people who study and reconstruct the climate of the past, have a lot of information about how climate change has occurred naturally and how we have adapted and the natural world has adapted to it in the past. And that is the wisdom that I hope to bring to bear. I've got a quote from Churchill, who my father thinks saved the world. But anyway, he would be pleased. The further backwards you look, the further forward you are likely to see. So we're going to start by looking backwards. So the basic course outline, class number 1, the basics. We're going to start by just talking about what climate is. It's a more complex topic than a lot of people realize. And then we'll move on to talk about the methods by which climate has been investigated and climate change have been investigated in the geological past. The history of our planet is, our planet's 4.5 billion years old, makes us feel young. And actually, a history of climate change, the well-understood history of climate change goes back only about 1 billion years, but we'll be looking over that 1 billion years. And that look over that 1 billion years will occur in the second class. So we'll look at the basic methods, basic definitions today. And then in the second class, we'll review what we know about climate history and climate change from roughly 1 billion years ago to yesterday. And then climate change and climate change in the future will be the very last class. And we'll look at what we know. It's going to be a little bit different than this. I'll start by talking about how we predict how climate might change in the future. And then we'll talk about the ways that we might adapt to that climate change and the natural world might adapt, using, in some cases, be unable to adapt, using what we have learned about the way the natural world and human beings have adapted to climate change in the past. Okay, so this is a little bit of information about me. There I am. I am a professor emeritus of geology. I taught at Hope College for, I think, 36 years. You can see that shirt has mineralogy and petrology. I started as what they call a hard rock geologist. I studied the chemistry of rocks and minerals that came from the deep core of eroded mountain belts. And we were trying to reconstruct the history of the deeper Earth. But in 1999, I started working on sand dunes, coastal sand dunes, first as a minor part of my research, but the coast of the Great Lakes has been my main research subject now for over 20 years. And, I've written about 20 papers on the subject, and most of the papers I've written in the last 20 years have been on that subject. Now, when I talk about paleoclimatology, I was fortunate to have a sabbatical at Lund University. There's a cathedral at Lund, and in a paleoclimatology lab where I learned some of the basic techniques we'll be talking about. So that's my background. By the way, if anybody has questions, I'll take questions during the process of the class, but you'll need to get the microphone from Linda so that the people online can hear those questions. So climate, what is it? Well, the World Meteorological Organization defines it as the average weather conditions for a particular location over a long period of time. Now, the WMO uses a 30-year period to determine climate. So when they talk about the climate of the area, they look at records over a 30-year period and then look at averages. Now, in that definition, there's a big thing that needs to be defined yet. Excuse me. Oh, what's missing? What do we need to know yet? Well, yes, and we also need to know what they mean by averages. And to illustrate why that's important, let's look at two cities, Seattle and Chicago. How many people think, which do you think? Is Seattle warmer than Chicago or Chicago warmer than Seattle? How many people say Seattle's warmer? Okay, how many Chicago warmer? How many would say that there's no difference in the average temperature between the two? And it's the second that is correct. The average annual temperature in Seattle is 52.4 degrees Fahrenheit. The average annual temperature in Chicago is 52.4 degrees Fahrenheit. Do they have the same climate? No, not at all. So we have to look at more than annual averages. We have to look at a lot more things to talk about climate usefully. One of the things we want to look at is climate range. In Seattle, the average coldest month, which is February, has an average temperature of 40.4 degrees Fahrenheit. The average warmest month in August has a temperature of 65.9 degrees. In Chicago, the coldest average month is January, 26.2 degrees Fahrenheit, and the warmest month is August, 76.4 and 76.7. And when the freezing point of water is 32, that difference in temperature range is very important, as we all know. So the NOAA, National Oceanic and Atmospheric Administration, which still sort of exists, it describes climate as being determined by the long-term pattern. So a pattern now, not just averages, of oceanic and atmospheric conditions. Now, if you want to describe that pattern, you use statistics. And the sort of statistics you use are means and extremes of things like temperature, precipitation, and other variables. But means and extremes don't capture everything we need to know about climate. It's also important to know the intensity, frequency, and duration of particularly extreme weather events. How stormy is it? How severe are droughts, for example, or floods? So this is also from NOAA, but I thought it was enlightening. Climate is what you expect. Weather is what you get. That's a quote floating around for a long time. But they illustrate it by saying if you're dealing with weather, that's what you're wearing today. If you're dealing with climate, it's what's in your closet. Okay, so how do we quantify and classify climate? How do we take these patterns and turn them into a classification of climate? Well, the most commonly used method is the Köppen climate classification scheme, which was developed by this Russian-German scientist, Köppen. There's his picture of it. He was the father-in-law of Wagner, Alfred Wagner. How many people have heard of continental drift and plate tectonics? Okay. So his son-in-law was a person who developed the theory of continental drift and considered one of the most influential geologists now of the 20th century. Köppen is considered one of the founders of climatology and paleoclimatology. And although we have modified his classification, the basic scheme was published in 1918. Here are the North American Köppen climate zones, Köppen Geiger, who modified his scheme a little. Here it is. Now, climate is particularly important because of the way it affects vegetation and therefore animal life as well. So he was interested in how climates, or classifying climates into the kind of vegetation that they were able to support. And in doing that, he came up with this classification. Now, if you take a look at Holland, there's a little blue streak that goes down by the lake. And we're in that blue streak. We're barely in what's called DFB, which is a humid, continental, mild summer, wet all year climate. Our summers don't always feel mild, but that's it. Now, a climate is DFB if it follows a number of statistical mathematical formulas. First of all, the coldest month has to average below freezing, 0 degrees Celsius and 32 Fahrenheit. All months with average temperature, all months have to have an average temperature below 22 degrees Celsius, 71.6 Fahrenheit, which our average temperatures do, at least did. There has to be at least 4 months averaging above 10 degrees Celsius, 50 degrees Fahrenheit. There has to be no significant precipitation difference between seasons, no wet season or dry season. And the average annual precipitation has to be greater than 15 inches. Now, I bring this up not because I expect anybody here to want to calculate a temperature, a climate, but to show you that what you need to know to classify climates are information about temperature and precipitation, both seasonal and annual. So we need to know at the very minimum, if we're going to characterize climate and therefore look at climate change, we have to have information on annual and seasonal temperatures over at least a 30-year period. And we need to have information over annual and seasonal precipitation. Now, if you want to characterize climate in more detail, now, my interest is in winds, the way it affects the coasts of the Great Lakes, the way it creates dunes, the way it causes erosion, etc. So particularly for me, when I'm looking at the climate history of an area, I want information on other things. And here are some of the other factors, if we want more detailed information, we need information on barometric pressures, which determine circulation of the atmosphere. Intensity, duration, frequency, and direction of winds. That's been the focus of my research. Intensity, duration, frequency, and the nature of storms, storminess. Storminess on the Great Lakes has been one of the main things that I've looked at. Intensity, duration, frequency of drought. Actually, turns out that aridity might be is very important in the response of the coast to climate. And then others. Have I left out anyone's favorite? Okay, so those are the sorts of things we need to know. Okay, now there's a problem there. We measure those things instrumentally. Well, the first measurement of relative temperature were done with something called a thermoscope in Italy around 1600, so 425 years ago, roughly. Here's a thermoscope. It's has to be open to the atmosphere. Tube with a bulb at the end is put down into a vat of water. Mercury was later used. Wine was sometimes used. Then when it gets warmer, the air in the bulb expands and it pushes down the water, wine, whatever. When it gets colder, the air in the bulb contracts and the liquid goes up the tube. And so you could take a look at the level of water in the tube and you could say something about whether it was warmer today than it had been yesterday, for example. Now, there's some obvious problems with this. Does anyone see one right away? Air pressure. Yes, evaporation would be a problem too, and air pressure definitely a problem. So this is also sensitive to barometric pressure. Before we look into how that's taken care of, I do want to note that in order to turn a thermoscope into a thermometer, all you have to do is add a scale. So you can say, today the temperature was 8 inches high. Yesterday it was 7.5 inches high. And later we can turn those into degrees, but you need some kind of scale. And there's some debate on whether the first thermometer was due to Galileo or to Santorio. Galileo claimed the first one was his, but Galileo was a very self-promoting, arrogant man. So, okay, so the early thermometers were very imprecise. They depended on air pressure as well as temperature. And calibration between these instruments was extremely difficult. So, two thermoscopes with slightly different designs would give you different results, even if they were side by side. So the first reliable, precise thermometer is due to this person right here, Fahrenheit. And we still, in the United States, say his name with every weather report. And it was developed around 1714. So we could do our first reliable measurements of temperature about 1714. Now, measuring rain's a lot simpler. And we have records from rain gauges that date back to 500 before Christ, BCE. But the earliest records from standardized rain gauges, so that rain gauges were constructed so that someone in the north of Korea would measure the same, and someone in the south of Korea could compare precipitation. That happened in the 1400s. And the first local systematic rain measurements in Europe date from about 1600. So precipitation in Europe began to be measured systematically about 1600, but only locally. which brings me to the scales about which we talk about climate. So we can talk about local climate, and that's the climate of a relatively small area, determined using observations from only a few weather stations. If we want to talk about the climate of Holland, we're going to look at information from basically three. There's a weather station in the airport, there's a weather station on shore, there's a weather station in town. So about three weather stations we'll be using. Regional climate is climate on a larger area. And to do that, it's determined from an aggregate of observations from many weather stations. And we've taken a look particularly at weather stations in the Great Lakes to look at windiness, storminess in there. On the Great Lakes alone, we have several dozen active weather stations. And global climate is the climate of an entire planet. And to do that, we have to use an aggregate of observations from throughout the world. And maybe later I'll talk a little bit about aggregating that data is kind of controversial. How do you put it together? And we may talk about that a little later in more detail. So if we're looking at regional climates, governments are involved in collecting that kind of data. The first person to systematically collect data in Europe internationally was the Elector of Bavaria, who sponsored the Societas Meteorological Palentina from 1780 to 1795. I dropped a one. Only 1,000 years. Look, the planet's 4.5 billion years old. Who cares about 1,000 years? But it's not until about 1850 that we began to get enough observations from enough places in the world and recording them that you can start talking reasonably about using that data to get a global climate. So if you're looking at instrumental measurements of climate and you want to look at climate change, you really have 175 years to do that over. And here's what the data looks like. On this graph, they're comparing everything with the average climate from the first 30 years. That's the zero line here. And they're looking at temperature change from that. And you can see, first of all, there's a lot of disagreements between data sets at first. The data sets converge as you get more information, more data. And, well, it's gotten warmer. That shouldn't be a shock. Some people dispute this, but I think almost every climatologist that I know of would say this is unarguable. The data says it's getting warmer. We know that. How much warmer? That's a little bit more controversial. This is just I ran into this and really liked it. Here's looking at temperatures throughout the various months, starting at the same time, 1851. And as you get redder and redder, you get warmer and warmer. So the data seems to indicate we're getting warmer throughout every month, throughout the whole year. Okay, so 150 years is, I think I may have, it's only 200 million of a percent of Earth history. So it's a trivial record. It doesn't go back very far at all. Now here is Köppen and his son-in-law, Alfred Wegener. In 1924, they published the climate of the geological past and started, well, they didn't really start paleoclimatology. The first realizations of ice ages did that, but they systemized it and tried to look at systematically at climate in the past. But they can't do that on the instrumental record. So what can we use if we want to know not only what the climate has been like since 1850, but what the climate was like during 1000 BC, for example, or what the climate was like 10,000 years ago, or a million years ago, or 100 million years ago, or as far back as we'll be going, which will be a billion years ago. How do we get that information? Well, we use something called proxy climate variables. Now, you have to remember, as a lecturer at Hope College, right now I'd be expecting students to write down all these definitions, and I would pause for a minute. I'll simply read them instead. Proxy climate variables are features that depend on some direct climate variable. For instance, something that depends on temperature, something that changes with precipitation, some feature that changes with the intensity and duration of winds. And hence, these variables can be used to infer something about those direct variables, infer what the temperature was, how much rain there was, how much wind there is. And looking at proxy variables, there are two kinds. One is historical and the other is natural. And we'll take a quick look at both of those. Okay, historical proxy variables come from the written records. And there are many, many of the things. People have recorded and written down things that depend on weather for a long time. And the first example I'm going to give is the quality of the grape harvest in France. Now, since the 1300s, there are records about whether this was a good year for a particular kind of grape or a bad year for a different kind of grape. It's critical because it affects the quality of wine, which in France is a direct reflection of the quality of life. Anyway, and here it is, the temperature deviations determined from the grape harvest. The quality of grapes depends primarily on the summer temperatures in France. But of course, there's something else that can affect this. What? Precipitation. So while temperature is the most important thing, precipitation plays a role as well. And we're going to find this out with many of these proxies. They depend on more than one climate variable. Now, this is one of my favorite, the timing of the blossoming of cherry trees. Now, in China, this has been recorded since 947 BCE. So we have almost 3,000 years of records from China saying when the cherry trees blossomed. In Japan, the records go back 1,500 years. And they depend primarily on spring temperatures. So we have this record of, late blossoming, cold spring, early blossoming, warm spring. And we can look at the relative temperatures during the spring in China going back 3,000 years. The recorded dates of the disappearance of sea ice off Iceland goes back 400 years. But if you're Icelandic, you rely on fishing and also on the ability for ships to go to Norway or Denmark and the trade that resulted. So in Iceland for 400 years, it was very important when the ships could begin to leave. And that's been recorded going back 400 years. And there are many, many, many such records. Um, Famines in Scotland, for example, both famines and dearths. Dearths are when people aren't starving, but they're hungry. Um, the record in Scotland goes back about 1,000 years. So, and many, many historical records allow us to say something about the climate in the past. The price of rye in Germany reflects how good the rye harvest is. And here's the record of the price of rye. This is the baseline inflation. Rye gets more expensive in general, but you see all these ups and downs. Now, when you have a bad rye harvest, rye's expensive. When you have a good rye harvest, it's cheaper. That's the paradox of being a farmer, right? The more you produce, the less your crop is worth. But, and those records go back to 1500. Now, what will determine the quality of the rye harvest? Temperature and precipitation. So it reflects both of those. Well, historical records have a disadvantage. They've got several disadvantages, but the primary one is they go back as far as written records go back. And continuous record, if you want a continuous climate record, you need continuous written records. In fact, so there are only a few places in the world where we have those. China is the great example. So a lot of historical data from China, because I understand that if you read Chinese, you can read a record from 3,000 years ago. You wouldn't have been able to speak to the person who wrote that record because you'd speak completely different versions of Chinese, but the Chinese written language has changed very little in that time. And some other parts of the world we have continuous written records, but they don't, by themselves, they would at most allow us to go back maybe 3,000 years. So we can use natural climate proxies. And those are from observations in the natural world. And one is the advance and retreat of mountain glaciers. Here's an example. This is the Rhone Glacier in the Alps. Here it is in 1870, and tourists would come and stay at this hotel. And in the summer, it would be really neat because there you're within easy walking distance of the glacier. How many people have visited a glacier? I mean, they're a lot of fun, right? So, and now, if you want to see the same glacier, here's your hotel. But you're going to have to go a lot further because the front of the glacier, this is a photo from 2008, is here. And these lines just mark different places where it had been. This is the 1870 position of the glacier. So the glacier's retreating. Well, glaciers depend on two things, whether a glacier advances and retreats. What two things? And precipitation, winter snowfall, to be exact. If you want a glacier to advance, you need a snowy winter and a cold summer. You want it to retreat, you have a warm summer and less snow in the winter. And well, we'll look at the record next time, but this has been happening throughout the world. If you've visited a glacier, you've probably seen that. Every glacier I've ever visited has clear evidence that it has been retreating. The width of tree rings. I wonder, what is that red line? Well, anyway. Yes, but they're in Alaska. So the width of tree rings. So, tree rings, you've got spring wood and summer wood. One is light and one is dark. Typically, you get rapid growth at one part of the year, and then slower growth. Slower the growth, the denser the tree rings, the darker they are. And then you have no growth for a large part of the year. So we've got spring, summer, spring, summer, spring, summer, spring, summer rings. But the exact width of those rings is determined by how much the tree was able to grow in that period. And if growing conditions are good, the tree grows a lot and you get wide rings. If growing conditions are bad, you get narrow rings. And these depend on temperature and precipitation. That's almost a litany right now during the growing season. Now, the beautiful thing about tree rings is that different trees have different conditions under which they thrive. So, some trees like it wet, some prefer it drier. Some need it warm. Some can grow well when it's not as warm. So if you've got a lot of different trees, you can begin to get even more refined information on growing conditions, temperature, and precipitation. Pollen from the sediments in lakes and bogs. Now, I've got a reason for bringing this up because towards the end, I'll talk about an actual example of some paleoclimatology work that we did, and pollen was an important part of it. But, pollen are these various spores that plants will release. So the pollen in lake sediments depend on what the plant community is, mostly upwind from the lake. And that also depends on temperature and precipitation. Okay, now is when we'll have to talk about isotopes. Isotopes in glacial ice are going to turn out when we talk about the temperature for about the climate in the last 100,000 years. This is going to be our most important proxy, and we're going to return to it again and again. So I want to describe how it works. First of all, we've got two kinds of particles that make up the core of an atom, the nucleus. Protons have a positive charge and neutrons have zero charge, but they both exist in the nucleus of an atom. Now, most of the chemical properties, almost all of the chemical properties of an atom depends on the number of protons it has. And of course, the number of electrons that surround the nucleus and balance out the charge. So if you've got two nuclei and they have the same number of protons, they are the same element, and they'll behave, in most ways, they'll behave the same chemically. They'll go through the same kinds of chemical reactions. But if you have the same number of protons, but the different number of neutrons, You have the same element, but they're different isotopes of the same element. And to give you a concrete example, let's take a look at oxygen. All oxygen atoms have 8 protons. Now, oxygen 16, this little number you're going to see up here, is the number of protons plus neutrons together. So oxygen 16 has 8 protons and 8 neutrons. Oxygen 18 has 8 protons and 10 neutrons. And there's also an oxygen 17, but it won't be as important for us. Now, chemically, they're almost the same, but in one way they are different. How is this oxygen went through the same kind of reaction? In fact, it's in the water molecule. You can see the Mickey Mouse ears on it, the hydrogen. Well, chemically, this is a water molecule. And they're going to be nearly identical, except for one thing. What's different between the two of them? Weight. They weigh different amounts. In fact, they're identical in most properties, except that oxygen 18 is heavier. Now, why that is important, chemically they'll behave pretty much the same, but there is one process, there are several processes, but one of the processes in which weight matters is evaporation. You know, evaporation, you've got these water molecules moving around quickly in water, and sometimes they start moving fast enough to go into the air. Well, it's harder, about 10% harder for this molecule to go to evaporate, to get in the air than this molecule. So water vapor will be richer in light, oxygen 16, than the water that's evaporating. And after evaporation, a lot of the O18 will be left behind, and the water left behind after evaporation will be heavier than oxygen 18. Now, starting in the 1950s, we began to be able to measure isotopes. They're hard to measure. And I'm a University of Chicago graduate. And the stable isotope work, geochemistry, was born at the University of Chicago. But it's turned out to have been critical in understanding past climates. And I'll go over why. There's someone coring a glacier. Actually, they're coring snow. But if you take a look at the snow or the ice in a glacier, you can measure the oxygen isotopes. It takes more energy for heavier water to go from liquid to vapor, so that at colder temperatures, fewer H2O18, heavier water molecules with heavy oxygen change to vapor. The O18 stays in the water. So there's less O18 in the precipitation, snow and ice that forms from that vapor. What that means, that if the temperatures are colder, you had less thermal energy in the sea surface, then your snow is going to have fewer oxygen 18 isotopes. If the temperature of the sea surface increases, there's more energy to kick those heavier water molecules out into the air. then you're going to have more oxygen astatine isotopes in the ice. So if we take an ice core, we can measure the oxygen isotope. And in warmer periods, the ice in the oxygen ice in the glacier, if the snow fell during a warmer period, is going to have more heavier isotopes. And if it was a colder period, it's going to have fewer heavier isotopes. So we can get a relative temperature. Now, there's a lot of problems with the use of climate variables, proxy variables, that have to be accounted for. And now I'm going to talk about them. I'm not doing statistics as was asked, but I am looking at some of the sources of error, some of the problems. And one of the first one of those is separating variables. We already seen that almost every climate variable I gave you depends on precipitation and temperature. Some more than others, oxygen isotopes less so. But so you've got to somehow say, is this tree ring, this thick tree ring, does that indicate a lot of rainfall or warmer temperatures or a combination of the two? And to separate variables, you often need many different proxy variables from the same area with different sensitivities to temperature or precipitation. Calibrating. So, oxygen isotopes tells us whether it was warmer or colder, how much warmer, how much colder. How do we calibrate that? And particularly if you want to compare temperature records from different parts of the world, you need to go from these relative hotters and colders to how much warmer and colder. Here's simply an attempt to do that for oxygen isotopes. And then dating. We want to assign ages to the proxy data. If you've got a climate record from Holland, Michigan, and you've got a climate record from Perth, Australia, and you want to look at the global climate, you need to know how they relate to each other. Are they from the same time as the one from Holland earlier? You need to date them. And here I've got an example of how we can do that. Should we take just a breath for a minute? I don't know what is the practice? Do people usually, in these hour-and-a-half classes, is it common to have a break or not? No, okay. Okay. When you teach college students for an hour and a half, you usually would give them a couple minutes in the middle of the class. Yeah. Okay. Now, this is a glacial ice core, two glacial ice cores. And one thing to note is that the color of the ice is not uniform. We've got light and dark layers in the ice cores. Now, when summer snow falls in a glacier, and a mountain glacier higher up, you will get snow in the warmer seasons, but when it's warmer, that snow tends to melt. And it forms a denser, darker ice. In the winter, it melts and refreezes and forms a denser, darker ice. In the winter, it doesn't, and it forms a lighter, less compact ice. So we now have, you know, summer, winter, summer, winter, summer, winter. Each pair is a year. So we can count them. And I know a friend of mine who worked on ice cores says he used to watch soccer games when he was counting these. Hopefully they checked them, or he watched very dull games. It would be very hard to watch a basketball game and count. Yeah. So that tells you when the ice formed, and the oxygen isotopes determine the ocean surface temperature at the time that ice formed. Put that together, and you can get a climate history that has actual dates. And here we are. The warmer, colder, warmer, colder, going back over 300,000 years from a particular ice core. Okay, the next problem is geographical scope. You're going to see this again next week, because this is the normally presented temperature diagram for the last roughly 12,000 years. Here's the, well, end of the glass glacial. It's actually about the beginning of deglaciation. 12,000 years ago, temperatures getting warmer, and then colder, warmer, colder, warmer. And you can, so this is usually the diagram you'll see if people talk about temperatures, climates in the past. And then at the very end, is there a laser pointer here? At the very end, temperatures are going up. The reason I bring this up is this is the data it's based on. Right here. There's temperature data in red from Southwest Canada, temperature data in purple from the Western US, Greenland in blue, Sweden in Svenska in green, Northwest Russia, Mongolia, East Asia. You can see how messy the data is. And this is going back only for the last roughly, 1,200 years. So it's only this part of it. But this is where most of the information came from, these places. So that's not global. What this is mostly giving us is the temperature history of the Northern Hemisphere, and particularly the temperature history of the northern part of the Northern Hemisphere. And most of the climatologists come from the northern countries of the Northern Hemisphere. As I said, Sweden's one of the birthplaces of paleoclimatology, and for example. So our coverage of the climates of the past is very rarely truly global. And most of the data we'll be looking at is biased towards the Northern Hemisphere, of course. personally, that's the most important part to us, but that's what we'll be looking at. Now, this is a good time for questions. I wasn't sure how long this was going to take, so I wasn't sure how much material to prepare. Now I have some idea. There are all sorts of teaching instincts that after, although I've only been retired for 6 months, I haven't taught in 4.5 years. So there are instincts that I discovered that are fade. This is a good time for questions. And then when we're finished with questions, I'm going to go through an example of paleoclimatology, a specific example done from our area.
Yeah, so my question is almost more like a public policy question. Glad to hear that you've been teaching up to about just a few years ago. Did you see a change in your students, let's say over the past 10 to 15 years? Because in my circle of friends, I have a few who say, "Doctor, this is bunk. This is a hoax." And we know it's just a hoax. How do you personally respond to that? And because of the public policy and this all became politicized, 10, 15 years, did you see it trending with your students?
Well,
And how do you respond to that?
well, certainly a change in student attitudes, because I've been teaching aspects of paleoclimatology and talking about climate change probably since the 1990s. So that goes into so for the last 26 years of my teaching career, it was an important topic, and it became more and more of a current topic on students' minds. Very few students ever challenged me. I get more challenges over the age of the earth. But most of the people who challenged me were folks associated with the oil business. But the thing is, we'll talk about climate change is much more complex than it's often presented. And part of that is due to the very narrow perspective of some of the physicists who do the work. But no person I know whose business is climate, and scientists can be a pretty skeptical bunch, will deny the fact that it's gotten warmer. You can get some arguments on why, although even there is a definite consensus. But nobody I know who seriously studies climate, who's looked at the data, would argue that the planet is not getting warmer. In my experience, and I hope I'm not offending anybody, the only reason to do that is you have a vested interest in denying it. And everybody I know who does that has a vested interest. Now, if you're going to have a hoax and perpetuated among almost all climate scientists, it's very hard to have a hoax if people don't have a vested interest. It's very easy to have a hoax, i.e. there is no climate change, when you do have a vested interest. So again, there is controversy on how much climate will change. There is controversy on what's causing that, or because it's complex and more than one thing is. But not much controversy on whether it's getting warmer.
Could you comment on what some scientists are putting forth, that the climate change is due to the tilting of the Earth on its axis?
Well, yeah, I mean, there's all sorts of reasons for climate change. So you have to separate climate change. The ice ages, the alternation, the glacials and interglacial periods, And we'll talk about these in more detail later, but sometimes glaciers have advanced, sometimes they've retreated. That is determined by the orbital characteristics of the Earth. The tilt and the axis, when during the Earth's orbit we're tilted away from the sun, when we're tilted towards the sun, how much we're tilted away from the sun, how much we're tilted towards the sun. All that determines whether you're going to have an ice age or not. But there are many other reasons for climate change. We'll talk next time about the difference between a hot house Earth and a greenhouse Earth. Sorry, an ice house Earth and a greenhouse Earth. In a greenhouse Earth or hothouse Earth, you don't have glaciers. And these are periods of time that last for tens of millions of years. And you have during what we call ice house Earths, you have oscillating glacials and interglaciers. So you have glaciers that sometimes grow and sometimes shrink. Now, the difference between a hothouse Earth and an ice house Earth has nothing to do with the orbital characteristics of the Earth. Glaciers and interglaciers do, but there are larger climate changes that don't. And so there's more than one reason for climate changes, for different kinds of climate changes. But some climate changes depend on the orbital characteristics of the Earth. That's one of the great advances in paleoclimatology, is realizing that. Interesting story. It's realized by a guy in a Nazi concentration camp. But anyway.
Is there any, is there any truth? I'm over here.
Oh,
Sorry.
You want
Is
me to
there-
go?
Is there any truth to the fact that we're currently at the end of the last ice age?
oh yeah.
So then the fact that our glaciers are disappearing is actually kind of natural?
Well, no, not necessarily. We're in an interglacial. But within an interglacial, you have the mountain glaciers have retreated and advanced in the last few thousand years. So the big glaciers are gone, but we have these smaller climate oscillations that cause the small glaciers, the mountain glaciers, to move forward and retreat, move forward and retreat. So while the retreat of the big glaciers reflects orbital characteristics of the Earth, the retreat of the small glaciers in that same period, in their advance, reflects different weather conditions. Hopefully that was clear. Next question.
Sure. My understanding in reading and seeing all the different glaciation periods that have happened, you said we were on an interglacial. My understanding is with Milankovitch factors and everything else historically, we should actually be getting colder. We should be approaching a glacial maximum, yet in fact, we're getting warmer. So isn't the data actually larger than it really is? Because we should be getting colder?
If you go back and read some papers in the 1950s, they were predicting we would enter a new glacial period based simply on orbital characteristics. I really don't know the quality of those predictions, but it has been predicted. Okay. Other questions?
I think we would assume that since the earth is round and turns and everything, that whatever happens at the North Pole also happens at the South Pole, and that the effects on ice glaciers and everything that you're talking about would be happening at each pole similarly. A related question that crossed my mind is, it seems to me offhand that there's more population of the earth that lives in the northern half of the world than in the southern hemisphere. Is that true?
Yes,
Just because of the land masses that are more toward the north?
yes, just among other things because of the land masses, but yes. Human population is tilted to the north.
Okay, does that mean that the research is more north oriented or biased than we don't care so much about the South Pole?
Yeah, we have ice cores from the South Pole. So, our ice cores come mostly from Greenland and from the South Pole. So we've got proxy data. There's a really interesting climate history of Australia that's been worked out. So we've got paleoclimate data. We've got climate data from the south as well as from the north. But our records and our focus is somewhat biased towards the northern hemisphere and particular parts of the northern hemisphere, Europe, North America. So, but we've got data from the paleoclimate data. There's paleoclimate data from Africa. I don't know of much from South America, but I think that's my ignorance, probably rather than the lack of the data.
I'm over here. Right here.
Okay.
Okay. Uh, in my college education at Hope, I learned that we're not infinite and that we are being slowly sucked into the sun, which is the end of all of solar systems. And so as we get closer to the sun, we're going to get warmer. How close are we getting and how is that different from, say, 100 years ago?
I don't think it's so much we're going to be sucked into the sun, but the sun will expand.
Either one.
Yes. But that has been a negligible factor in geological history. I mean, more interesting is the fact that the day has slowed down. Days have gotten longer. Yeah, I mean, if you guys had been here in the Precambrian, you might have had, I'm not sure when, but maybe only 12 hours to your day. Just so. But I don't know, that will change climate to some extent. But in the recent past, those kind of major changes. Now, we know that the amount of energy that sun puts out fluctuates. Sometimes the sun puts out more energy, sometimes it puts out less. Now, now I'm working from memory of stuff that I haven't worked on, but there is some, and we know that since we've observed solar cycles, but we've only been observing the sun really for a century and a half. And we know within that period, sometimes the sun gives out more energy, sometimes less. There's good evidence of longer cycles. I have an acquaintance in the Free University of Amsterdam who works on peat bogs in the paleoclimate record from peat bogs. And they've looked at the same time, they'll reconstruct the climate from the kinds of fossils they find in the peat bog, pollen and macrofossils. They've been measuring cosmogenic isotopes. And so cosmogenic isotope is the stuff that comes from the solar wind. So, and some of it reaches the surface of the planet. So when you've got a lot of solar wind, a lot of solar activity, you have more cosmogenic isotopes and a different ratio of isotopes than when you have less. And he is convinced, and his data is pretty good, I don't think it's gotten enough attention, that he can correlate some major climate changes with fluctuations in the cosmogenic isotopes. In other words, some of the things that drive, one of the things that drives our climate change is whether the sun's putting out more energy at a particular period of time or less energy. And there is some evidence, and that's one of the competing hypotheses for the warming we're seeing is some people say what you're really looking at, or at least in part, usually not in whole, but at least in part, we're looking at an increase in the solar output. So that's what I'll try to get more information next class period on that. Okay,
Thank you.
other questions?
This is a very recent question, but how far do we have data about lake levels in the Great Lakes? How far back?
Oh, that record is beautiful. I wish I could show it to you. Actually, maybe no, I think I cut it out of this paper. The parts of the paper I was going to show. This is optional, by the way. This just goes over some details of some work done here. We go back about 6,000 years pretty well. It's due to a group of people who work for the Indiana Geological Survey, which, you know, Indiana has only a small lake, amount of lake, but Todd Thompson, who works for the survey, which is down in Bloomington, not Bloomington, where is Indiana University? Bloomington, yeah, that's right, down in Bloomington. He had an interest in that, and they've worked on the lake histories. What they've used are bays that trap sediment. So, you know, there's some bays we have where they keep trapping sediment. And in that trapped sediment, they have evidence, they have proxies that can tell them where the lake level was at different times. And there's been in the last 6,000 years, there's been a decrease in lake level, but on top of that, there have been ups and downs and ups and downs and ups and downs. And no, that is a really detailed record. Now go back further than 6,000 years, and we know that there have been periods of, we still have a lot of information on lake levels, but it's a lot coarser. We're no longer talking about knowing the lake levels changes on the scale of decades, but on the scales of 50 or 100 years. But it's a good record. Other questions?
Yeah, what about the gases in the atmosphere? You haven't talked about CO2, you know, that greenhouse gas and other gases from, big geological events.
The emphasis is entirely on CO2, which traps infrared radiation, and the main way our planet cools is by giving off infrared radiation. You're giving it off now. Everything that's warm gives off infrared radiation. And what CO2 does is slows down the escape of that infrared radiation from the atmosphere. So it's just like putting a blanket on you. The blanket doesn't create heat, but it slows down the rate at which you lose heat. And the physics behind that is well understood. And there's a fair amount of evidence in the geological past that of a correlation between the amount of CO2 in the atmosphere and the temperature. For instance, I mentioned briefly hothouse Earths, where you know, where when hothouse Earth is, we'll find next time you don't have glaciers, you don't have ice at the poles, for example. The last real hothouse Earth would have been spanning the end of the dinosaurs extinction. So we're talking about tens of millions of years ago. But there's evidence that there were real high levels of CO2 in the atmosphere at that period. And we'll look at the ice core evidence that shows a correlation between temperatures as recorded by oxygen isotopes and the amount of CO2 trapped in bubbles in the ice. So it's a good correlation. CO2 is one of the many factors. Solar radiation, the amount of CO2 in the atmosphere, the tilt of the Earth's axis. There are many, many things that drive climate change and climate. Other questions? Over there?
I guess my question is, what can we do about it? About the CO2 levels and that kind of thing. We're all working on that, but that isn't the only factor. You know, what else can we do as
Well-
humans?
Well, now this is a personal opinion. There are two ways we could try to stop climate change, and we should moderate it. So I think the less CO2 we put in the atmosphere, the better. We can try to adapt to climate change, and we're going to have to use a combination of strategies. And in the last class period, we'll talk about how hard it may be now to adapt. But let me say this, as far as adaptation is concerned, where if you were sitting in this classroom 12,000 years ago, how would it be different than now? Anyone? You'd be under about half a mile of ice. So we've had this tremendous climate change. This is a preview of some things we'll talk about, but in deglaciation. It's a huge climate change. It's larger than the climate change that we're experiencing, that we're predicted to experience. There are differences on rates and things, but humans adapted, most of the natural world adapted. And so I think our strategy is going to have to be a combination of trying to mitigate the things that cause climate change and adapting to it. And we can discuss in more detail the things we can do to that. Obviously, the less carbon dioxide we put into the atmosphere, the better. But that might address not all of the climate change. A portion of the climate change might be due to an increase in solar radiation. To that, we'd have to just adapt. Yes.
Is it not completely clear that the gorilla in the room is the increase in carbon dioxide in our atmosphere? And all of these other variables, though they are contributing to climate change, that it's pretty clear scientifically that it's the CO2 that we are introducing into the atmosphere since the Industrial Revolution began that is the primary cause of the concept of increased temperature.
That's definitely the consensus opinion. The main question is whether solar radiation has got a component in it or not. So, but there's no doubt CO2, the consensus among scientists is, climate scientists, is that the carbon dioxide in the atmosphere is probably, and most would say definitely, the primary driver.
And the carbon isotopes in our atmosphere clearly demonstrate that the extra carbon has come from the combustion of fossil fuels.
Oh, yes, there's no doubt about it. In other words, most of it's dead carbon.
Right.
Right.
So of two things we could do in Holland, Michigan, just to observe climate change, which would be more significant among these two? Number one, go to the beach and look at the water and the sky and the level of the skyline and learn things about the ocean. Versus go to the train station, or the next time you get hung up by a train passing by and you have to spend 10 minutes watching a train go by, count the coal cars. The trains that go through Holland have an unbelievable number of coal cars on them. Where is that going? Where does it come? And that's the culprit right there.
It's one of the major culprits. I mean, burning coal creates more CO2 than any other fossil fuel. You know, I'm surprised nobody asked me about a climate proxy we have right here. Our record doesn't go back hundreds of years, but the timing of the tulips is a climate proxy. Anyway, yes.
The CO2 blanket that is covering the earth now and getting thicker, does that tend to block solar radiation as
No,
well?
it blocks the radiation coming from the surface of the earth. It's transparent to solar radiation. So it's the radiation coming in that heats up the earth. So by the way, if you block that solar radiation coming in, or if you radiate it directly back into space, then the earth heats less. And ice does that. So but I'll go into that later. But what happens once the planet heats up is it begins to lose heat, radiating infrared radiation. And that's what carbon dioxide interferes with. And what it does is slow down the rate at which that radiation exits the earth, exits our atmosphere. So we retain the infrared radiation, i.e. the heat longer than we would otherwise. In other words, it's insulation. And it's a good thing we have it. Get rid of all carbon dioxide and we'd be in the atmosphere, we'd be back in another ice age. Other questions?
Well, if not, everybody please come back next week and we'll continue this discussion, and let's all give Ed a round of applause for being with us.
Next week, we'll look at the climate record for the next the past billion years, and we'll deal with some of these issues: solar radiation, carbon dioxide, etc. Again at that time.